There is a $4 bag sitting in the hardware store right now that will pull more moisture out of your air in 24 hours than a $300 electric dehumidifier running on your power bill. No moving parts, no electricity, no filters to replace every 3 months at $40 a pop. Just raw chemistry doing exactly what physics tells it to do, working silently, relentlessly, and with an efficiency that the appliance industry has spent decades making sure you never fully understand. That is what this is about today. Phase physics, the science of how certain minerals interact with atmospheric water vapor at the molecular level, and why that knowledge is worth infinitely more than whatever plastic box a salesman is trying to put in your cart. The survival and home improvement industries have spent decades convincing you that humidity is an electricity problem, that the answer to moisture in your basement, your bug-out location, your gear storage, your food cache, is a compressor-driven appliance drawing 300 to 700 watts of continuous power, cycling on and off, draining into a bucket you have to empty every 2 days, requiring maintenance, replacement parts, and an uninterrupted power source. They built an entire market around that premise, a market worth billions of dollars annually. And like most billion-dollar markets built around a perceived necessity, it is propped up by a foundational lie. The lie is this, that removing moisture from air requires mechanical refrigeration, that you need a cold coil to condense water vapor, a compressor to maintain that temperature differential, a fan to push air across the coil, and a drain system to remove the collected water. That is the only serious solution. That is what works at scale. Everything else is just a novelty. That is what the industry tells you. And most people, because they have never been given a reason to question it, absorb that mess, sage, and go buy a dehumidifier. But here is what nobody in the appliance aisle ever tells you. Water does not just sit in your air randomly. It moves according to pressure gradients governed by something called vapor pressure differential. The air around you right now contains water molecules in a gaseous state, suspended at a concentration determined by temperature and the partial pressure of water vapor in that space. When the relative humidity in a room reads 70%, what that actually means is that the air is holding 70% of the maximum water vapor it can physically contain at that temperature before condensation begins. It is not a static number. It is a dynamic equilibrium between evaporation and condensation happening constantly at every surface in the room. Now here is where phase chemistry enters the picture. Certain crystalline compounds, specifically hygroscopic salts, have a property called deliquescence. Deliquescence is the process by which a solid material absorbs water vapor from the surrounding air until it dissolves into a saturated liquid solution. The driving force behind this is vapor pressure. A hygroscopic salt like calcium chloride generates a vapor pressure at its surface that is dramatically lower than the vapor pressure of the ambient air around it. We are talking about a surface vapor pressure as low as 6 to 10 millibars at room temperature, when ambient air vapor pressure might be sitting at 16 to 20 millibars. That differential, that gap between the pressure at the salt's surface and the pressure in the surrounding air, is a thermodynamic imbalance, and physics, as always, will not tolerate imbalance. It resolves it. Water molecules migrate from the high-pressure zone, meaning the air in your room, toward the low-pressure zone, meaning the surface of the salt, at a rate determined by the magnitude of that differential. This is phase change absorption. The water vapor undergoes a phase transition from gaseous state to liquid state, not through refrigeration, not through mechanical condensation, but through direct chemical uptake driven purely by the thermodynamic properties of the compound. No compressor required, no cold coil, no electricity. The physics runs the process. The salt is the engine. Calcium chloride has one of the highest water absorption capacities of any commercially available desiccant compound. A single kilogram of anhydrous calcium chloride can absorb between 0.6 and 1.0 kilograms of water before reaching saturation. Put that in practical terms. 1 kilogram of this material, in a properly ventilated container, can remove the equivalent of 600 to 1,000 milliliters of liquid water from your air. And the absorption rate is not linear. It accelerates as humidity rises above 70% relative humidity, which is exactly the threshold where moisture damage to gear, food stores, electronics, and structural materials begins occurring. The physics delivers peak performance precisely when you need it most. Walk into any big box store and you will find a wall of electric dehumidifiers priced between $180 and $450. The mid-range models, the ones with the decent capacity ratings, sit around $280 to $320. They are rated at 30 to 50 pints per day under controlled laboratory conditions, which means at 80 degrees Fahrenheit and 60% relative humidity, a scenario that bears limited resemblance to the conditions in your actual basement or storage space. Real-world performance in a cooler, less-than-ideal environment drops that rating by 30 to 50%. Add in the operating cost. A compressor-based dehumidifier pulling 300 watts of continuous power costs roughly $0.80 to $1.20 per day to run at average U.S. electricity rates. Over a year, that is $290 to $440 in electricity alone, on top of the purchase price, on top of the filter replacements, on top of the inevitable compressor failure that hits around year 4 or 5 and turns your $300 investment into landfill. Now look at calcium chloride. The material goes by multiple commercial names: ice melt, road salt, pool chemical. Walk into a hardware store and you will find it in 5-pound bags for $4 to $7. Industrial bulk suppliers sell it by the 50-pound bag for $15 to $25. The anhydrous or flaked form, which has the highest hygroscopic activity, is the one you want. It has no power requirements, no moving parts to fail, no filters, no refrigerant, no compressor. Its operational cost over a year in a passive desiccant system is close to zero, because once the calcium chloride absorbs to saturation and becomes a liquid brine solution, you can either replace it with fresh material at the same $4 cost, or in some configurations you can actually regenerate it by evaporating the collected water through gentle heating, returning the compound to its anhydrous state and making it ready to absorb again. What you need is calcium chloride in flake or pellet form, a 5-gallon bucket with a lid, a drill, something to elevate the inner container, and about 15 minutes of setup time. Here is the build. Take your 5-gallon bucket and drill a series of half-inch holes around the bottom third, roughly 20 to 30 holes spaced about an inch apart. These holes are your moisture collection drainage system. Now take a second smaller container, something like a mesh colander, a plastic strainer with fine holes, or a fabric liner suspended inside the outer bucket. This inner container holds the calcium chloride. Load it with 2 to 3 pounds of calcium chloride flakes. Do not use the compressed pellet form designed for ice melt applications on driveways, because those often contain additives that reduce hygroscopic efficiency. Buy the food-grade or pool-grade calcium chloride if available, or the pure flake form marketed for water-softening applications. The inner container needs to sit elevated several inches above the bottom of the outer bucket. You can use PVC pipe sections, wooden blocks, or any non-reactive spacer material to achieve this. The collected liquid brine, as absorption proceeds, needs to drain away from the active desiccant mass. If the calcium chloride sits in its own collected brine, absorption efficiency collapses because the brine itself has a vapor pressure that equilibrates with ambient humidity rather than driving continued uptake. The physical separation between the active desiccant and the collected liquid is critical to maintaining the vapor pressure differential that powers the system. Place the assembled unit in the space you want to dehumidify. The optimal positioning is on a shelf or table that allows air circulation around the unit on all sides. Maximum height in the room is actually counterproductive because warmer air near the ceiling contains more water vapor, which sounds like you want the unit there, but the floor-level cooler air is where condensation damage begins, and the vapor pressure differential drives moisture from throughout the room toward the collection point anyway. Mid-height, with clear air circulation, is the sweet spot. In a space up to 500 square feet, 2 to 3 units loaded with 2 pounds each will achieve meaningful humidity reduction within 12 to 24 hours under high humidity conditions. Independent testing on hygroscopic passive desiccant systems versus compressor-based electric units consistently shows something the appliance industry does not want published in its marketing materials. In spaces below 60 degrees Fahrenheit, compressor-based dehumidifiers lose between 40 and 60% of their rated capacity because the refrigeration cycle becomes less efficient as ambient temperature drops. Passive calcium chloride systems, operating on vapor pressure physics, are largely temperature independent in their absorption characteristics down to about 50 degrees. In a cold basement or a winter storage space, The passive system outperforms the electric unit per dollar invested by a factor of 3 to 4. The military has known this for decades. Field logistics for stored equipment and ammunition in cold, damp environments have used calcium chloride and similar hygroscopic desiccant packs extensively since the mid-20th century, precisely because of this temperature stability advantage. At peak absorption efficiency, properly deployed calcium chloride in a passive collection system can reduce relative humidity from 80% to between 50 and 60% in a 300 to 400 square foot sealed or semi-sealed space within 24 hours. That is not a trivial number. 50 to 60% relative humidity is below the threshold where most mold species can establish growth, below the threshold where most common hardware and electronics begin accelerated corrosion, and below the threshold where stored food moisture content begins degrading shelf life. You just hit all three critical survival storage thresholds with a $4 investment and zero electricity. The regeneration cycle extends the value further. When your calcium chloride has absorbed to saturation, you will notice the inner container holding mostly liquid brine rather than solid flakes. Take that brine, transfer it to a shallow pan or a tray, and apply gentle indirect heat. Direct sunlight on a warm day, an oven set to 200 to 250 degrees Fahrenheit with the door cracked, or even a dehydrator set to medium temperature will evaporate the collected water and leave behind concentrated calcium chloride crystals that can be collected, dried fully, and returned to service. You are not spending $4 every cycle. You are spending $4 for a potentially indefinite supply of passive dehumidification capacity, limited only by your patience with the regeneration process. For a survival cache or a prepper storage space, think about what this actually means. You can dehumidify your entire stored gear inventory passively, with zero power draw, using material available at virtually every hardware store in the country for less than what a single dehumidifier filter replacement costs. You can scale it trivially, adding units as your storage space grows. You can deploy it in a vehicle, in a storage unit, in a root cellar, in a shipping container, in a tent or a tarp shelter, anywhere that humidity is threatening your supplies or your equipment. The system has no failure modes tied to electrical components. There is nothing to burn out, nothing to short circuit, nothing that requires a replacement part you might not be able to source 6 months into a serious disruption scenario. You just learned something that took industrial chemists decades to figure out, and that appliance manufacturers are actively motivated to keep you from knowing. The fundamental physics of moisture management is not a mechanical problem. It is a chemistry problem. It is a thermodynamics problem. And thermodynamics, unlike a compressor, never needs a power outlet, never breaks down, and can be purchased for $4 at the hardware store. The survival community talks endlessly about food storage, water purification, medical supplies, and defensive tools, but humidity quietly destroys all of it. Mold in your food stores, corrosion on your tools and weapons, condensation in your electronics, moisture damage in your medical supplies. The mineral that protects all of those things from the invisible threat costs less than a cup of coffee. The question was never whether you could afford the solution. The question was whether anyone was going to tell you what the solution actually is. Now you know. And what you understand about vapor pressure differentials and phase change absorption today is something most people, including most preppers, are going to keep paying $300 to not understand tomorrow.